everybody. Listen, the technical team advised us to tell you that you should all stand up and kind of shake your legs so you're all awake for the last talk. Okay, come on. Come on, because our time is counting here, you know? Okay, okay, everybody's awake. I'm not sure if we did that right. Oh, okay. Yeah, so thanks for coming to our talk. I know it's the last one of the day, and it's actually the last one for BlueHat, so we'll try not to keep you here for past happy hour, right? So our talk is staying sharp and bringing covert injection tradecraft to .NET. I'm working on IBM's Red team, X-Force Red, and we're doing adversary emulation, or for me it's more simulation, if that distinction makes sense. And the goal is hopefully to make our clients better prepared for when adversaries eventually come along to steal all their stuff, basically. Their money, their IP, all of that stuff. I should mention as well, as it has some relation to what we're talking about, that I was working for FireEye before on the Tor team. So if there are any defenders, I know the pain you feel when you have to put out fires every day. Left, right, and center, and develop detections that scale, you know, that don't break your environment or your client's environments, okay?
And I'm the Wover, as known on the internet. I do adversary emulation for my job and write open source tooling on the side.
Okay, short and sweet, I like that. So why are we talking about in-memory tradecraft? And there's like kind of two stories to that, okay? The red team story and the blue team story. So on the red team side, we've been using in-memory tradecraft for a long time. It's not like a new thing, right? Think about Stefan Fewer's reflective DLL injection. But we've not always been good at keeping that tradecraft up to date. Why? Mostly because what we've been doing just works, right? Nobody is picking up on what we're doing. However, that situation is like changing the last 2 to 3 years. A lot of security vendors and products are getting better, at least some of the vendors, okay? We're not going to name any names. So you have things like breaking parent and child relationships, right? So those detections can go out the window. There's no magic, right? You just call create process with like startup infox and specify the parent. Or some undocumented functions like nt create user process and specify a handle. The other thing is command line argument detections can go out the window as well. An attacker can spawn a process with innocuous arguments in a suspended state, and then your logging infrastructure picks up all of that data, and then the attacker comes in and rewrites the PEB, and then when that process is resumed, malicious arguments execute, right? You also have in-memory evasions that have been added. So when Cobalt Strike reflectively loads a module, you can stomp the module headers in memory. Presumably, some memory scanners are looking for some of that stuff. And finally, you have so-called module stomping, where you can load a legitimate module into the process and then override it with the malicious module, right? And then when that module executes, it looks like it's coming from that legitimate module. We have something similar we're going to talk about later today. The Wover will discuss that in more detail. And then on the blue team side, it's pretty simple. Offense informs defense, right? So changes in offense either through our security community or malicious actors highlight problem areas, and then defense kind of adapts and creates visibility or data that defenders can use in those areas. Good example is AMSI. So first, there was AMSI in PowerShell, then it came to Office for phishing payloads, and now it's in .NET, right? Why are we talking about this today and releasing some tools? One of the reasons is that defenders need models they can use to reproduce that tradecraft and develop detections, okay? Now, these things we're talking about are not like net new techniques. Okay, threat groups are already doing these things, and unfortunately, I should tell you that even like some low-rent crypto miners that we might consider to be trash, they are doing that as well because they may be purchasing loaders from the black market or whatever they do, basically. Final point is not super important, but it's just a note that whenever you can, as a defender, you should focus on principles and primitives to catch behavior instead of signaturing tooling, right? I'm not saying you shouldn't signature tooling. You should, okay?
So specifically, we're going to be talking about doing in-memory tradecraft using .NET. So .NET has been used by adversaries a lot using C# to write your malware. People thought you were probably a skitty. But it's changed recently. .NET has become a lot more powerful. It's the preferred platform for development on Windows for application development. As such, it has access to a lot of APIs, both .NET APIs and access to the underlying Win32, NT, COM APIs, all the other normal APIs available on Windows. As .NET has become more powerful, so has the malware that's leveraged it, and the modern .NET malware as well takes advantage of features that are specific to .NET and not available in other APIs. The main reason people are able to abuse it so easily is that in like 2 lines of code, you can load and execute a .NET assembly, which is a .NET exe or DLL, from memory and execute it without touching anything on disk. And that's not a bug, that's actually a feature of .NET for some reason. So it can be run from memory. It's hard to inspect at scale across the whole enterprise. Also, the reason people have shifted to it recently in the past year for a lot of their post-exploitation is they have been relying on PowerShell for the past few years. A lot of attackers have been using PowerShell and getting away with it, but recently when, Microsoft has added a lot of introspection to PowerShell. They've added script block logging, module logging, command logging, AMZ. With all of these new features, it's getting harder to get away with using PowerShell, even if you're doing it from memory. So as such, because PowerShell is .NET, and writing in C# or whatever other .NET language you want is also .NET, you just have to go a layer deeper from PowerShell, and now you can still load your tools from memory, but you're not subject to all of the introspection of PowerShell. So this is what they're doing. They have added AMZ to .NET assembly loading now in version 4.8. That's not installed on everything, and it can be bypassed in some ways. The other thing is C# or whatever your preferred .NET language is really easy to develop in. There have been a lot of new toolkits released that leverage .NET. Some examples are Covenant and Silent Trinity, which are used by red teams and also by some real-world threat actors. And it's important to note that everything we're talking about here, there are no 0 days, there are no exploits per se, there are no bugs. All of these are abuse of legitimate features for post-exploitation and executing on target covertly. So the other thing is that even though you can load the stuff from memory, if you inject .NET assemblies or .NET code into a process, you will still get some anomalous behavior. Part of why we've been doing this work is to provide options for tool developers to reduce that noise, but you do get some anomalous behavior, especially assembly image loads and module loads. So everything we're talking about as well are existing TTPs. They've been used for years. They've been observed in the real world. We're not showing anything new, though we do have some new twists on things. The other point that I was going to make was that because attackers are using .NET for post-exploitation a lot of times, so say they have some interactive toolkit, they have an implant already on the system, all of their post-exploitation tools are .NET assemblies. Because they're using that for all of their post-exploitation, that can be a single point of failure. So if you can catch it reliably, then it can be a pretty good detection mechanism to catch whatever they're doing after they've gained access. So specifically, all the work that we've been doing has been put into Sharpsploit. Now, Sharpsploit was not originally created by us. It was created by Ryan Cobb at SpectreOps. It is a library of post-exploitation tactics, techniques, and procedures. It's been integrated into many remote access tools, many implants, both used by real-world adversaries and created by red teams such as Covenant. Covenant, we actually aren't going to show the demo because of time. However, it's a .NET-based command and control framework that allows you to write C# scripts, sort of like you previously would be able to use for PowerShell, and run those, dynamically compile them, send them to an implant, load it from memory. But it has access to Sharpsploit, so all of the post-exploitation tasks have access to Sharpsploit as a library for techniques.
Yeah, okay, so you already got like kind of an introduction on Sharpsploit, right? So in these slides, I just want to briefly explain some of the core principles of dynamic invoke. That's probably not the right term, but You'll see what I'm talking about. So the first thing is we are ++ undocumented. Okay. So whenever we're using APIs in dynamic invoke, we're always at that undocumented layer, right? You can see an example here of a kind of API call sync. So usually you have documented APIs that call into extended APIs and then call into undocumented APIs. You may ask, like, why are we doing that? And there's two reasons, simple reasons. A lot of times, undocumented APIs give you some easy access to functionality that you don't have in the documented version, or you simply don't have those features at all in the documented versions, right? That's one reason. And the other reason is if you are facing some kind of security product which is doing hooking, hopefully, statistically, if you're here at the undocumented layer, you're going to be evading some percentage of detections, right? If somebody is hooking load library EXW, you'll be fine, right? Just some percentage game that we're playing. Now, in dynamic invoke, we're not using pinvoke at all. The Wover will talk a bit about why that is later, but the question is, how do we replace that functionality? So we use our, or at least my most favorite class in .NET, the Marshal class. I love it, okay? And we're using getDelegate for a function pointer there. So if you're unfamiliar with how that works, a delegate is kind of like a definition for a function. You have like a return type, the arguments, and the argument types, and then if you have a pointer to a function, you can say, this pointer is like this delegate, essentially, and then you can just call that function as normal. And that gets us around using pinvoke. However, we need to be able to resolve function pointers, so we're just doing some stuff there to do that manually, okay? So normally, you'd call like a load library, and then you'd get a handle to the library, but that's really a base address, right? It's not a real handle. And then you'd call getProcAddress to get the address of the function. So we need to replace these two components, okay? So for load library, what we can do is just simply read the process peb. All of these entries are not super important, but you have like peb LDR data structure, which has some linked lists of modules that are loaded by the process, such as the inload order module list, and then if you loop that list, you can get all the modules that are loaded by the process and their base address. So that kind of replaces the functionality of load library, and then to actually get the address of the functions we're interested in, you can just do some pointer math in the PE. You check out the PE headers, you find the image export directory, and then you can loop all of the exports of that module, right? Kind of like, I'm sure you've seen that in malware if you're in defense, so we're just on par there, okay? And then you can look up by name, by ordinal, and I added like HMAC MD5, which is like a keyed hash lookup that you can do. Okay, yeah, one of the core features of dynamic invoke is the ability to manually map executables and DLLs and call them either by their entry point or by DLL main, process attach, right? And also call exports of DLLs, etc. So I implemented a manual mapper, which is more work than it seems. It's a bit crude currently. It needs a bit of loving, okay? But it does the work mostly, right? You can kind of see the process here. You allocate the size of the image from the optional header. Then you write the header, the sections. Then you have to relocate the module because it's not going to be at its preferred base. Then you have to fix the import address table so that any functions from that module can be resolved. And then you have to set the permissions, right? So like the headers are read-only. The text section is read, execute, etc. And then the last thing that we wanted to do was implement a generic syscall wrapper. So syscalls are great if you can use them operationally. But the problem is that syscalls, the call stubs for those syscalls change slightly from OS to OS, and most certainly between 32 and 64-bit and on WoW64, right? That's one problem. And the other problem is that syscalls are essentially identified by an ID, an integer, and that integer is changing all the time. So we don't want to maintain lists of those integers like on Jeru's website. So what we're doing here is we already have functionality to manually map. So we're mapping a duplicate of NTDLL into the process, and then we can just resolve the address of that syscall and copy out like 50 bytes or 60 bytes into our process as RX. And then we can just call that syscall normally. Why are we mapping a duplicate? The reason is that your security product may be hooking those syscalls. So if you're copying from NTDLL that's already loaded by your process, you may be copying those hooks as well.
So why did we go to all the effort of developing deinvoke? So specifically, this was designed to give offensive tool developers options. So say you're writing some post-exploitation tool, you want to be able to determine how you reference unmanaged API calls. Normally, if you're just using pinvoke, then there are two main indicators that are a result of that. First of all, if your .NET assembly is dropped to disk, then you'll have a static reference in your IAT of that .NET assembly. So anything that scans that executable on disk will see that reference. But additionally, as well, you're making calls to the API calls that you're referencing, which will be caught in any hooks. So we wanted to give tool developers the option in how they reference those that avoids pinvoke. So one of the main things that you want to avoid is image load events. So when you've injected into a process and you start running things from that process, you're going to generate image load events, or otherwise known as mod load events. You want to avoid generating mod load events that are anomalous for that process, especially if you've injected into a legitimate process, a process that normally runs on Windows. You don't want to start loading things that process has never in history loaded before. That's pretty anomalous. So using manual mapping, you can instead map your own copy of whatever DLL that you want to use and reference calls from that, completely bypassing any hooks that have been placed in the normally loaded versions of those modules. Or you can walk the PEB, which will bypass some versions of API hooking. So generally speaking, the options that we provided allows you to bypass many types of API hooks. With manual mapping, you can theoretically bypass all of the user land versions of API hooking. Although you won't bypass any hooks that the module you've mapped is like if it's referencing another module that's already loaded and there are hooks in that module, then of course you'll still trigger those. But any calls that you make into the module that you've manually mapped will not be hooked. So the other things is that you want to avoid memory scanners. Now, manual mapping is nice because you can avoid the API hooks, but it comes with the downside that now you have this giant PE file just sitting around in memory, which is not normal. So if you want to avoid memory scanners, you're going to have to find ways to hide your code into what appear to be more legitimate parts of the memory in your process. There's a good blog post by Forrester Orr about how to do this with shellcode, where he hides shellcode in the exports of legitimately loaded modules. So when you call that shellcode, it looks like you're executing a legitimate export of a DLL. So the other thing is that you want to, when you manually map that module into memory that's backed by a file on disk. So normally, if you just manually map, you're mapping the DLL into dynamically allocated memory. Generally speaking, if you're dynamically allocating code into memory and then executing it, there's some sort of injection going on. That doesn't normally happen. So you want to be able to hide your code inside of legitimate modules. So specifically, when you're using deinvoke, you should always try to use deinvoke whenever possible rather than pinvokes to avoid those static imports in the IIT and those image load events. Don't use load library because that will be subject to API hooks. Instead, use map module to memory. So that's the manual mapping function that we've added. It lets you point to a file on disk, and it will manually map that, and then give you the address, the base address of where it's been mapped into memory.
There are overloads as well to give it a byte array, so you can just give it a byte array instead of a file on disk.
Right. So most of the stuff, we have an option of being able to manually map from disk or manually map from a byte array in C#. So also avoid get proc address. We provide a function we call get export address, which regardless of where a module has been mapped into in memory, it will walk the export table of that module in memory to find the API call that you want to use, and then it will give you a pointer, which you can then use to pass to deinvoke and call that, passing in whatever function signature you want, returning whatever type of variable you want, passing in whatever arguments you want. Additionally, that function is provided with dynamic function invoke. There's also dynamic API invoke, which automates a lot of this process, so you don't have to go manually find all that stuff. It will look in the PEB or the currently loaded modules or load the thing using load or load DLL if it's not already been loaded. It just doesn't do the manual mapping. That you're going to have to decide to do on your own. So one component of this is module overloading. We talked about hiding a module in disks, but how do you actually do that? It turns out that ntcreate section, which is a syscall, has these options, sec image and a file handle. If you pass in a file handle and the special sec image flag, it will actually map that file into memory, file-backed memory, doing a lot of the work of normally loading any module. It doesn't use the normal load or load DLL, but it does generate an image load event. So you create a section from a file, passing in that special flag, then you map a view of that shared memory section to either your current process or a different process, and you will have a copy of that module in memory. Now you have access to some file-backed memory. So from there, you overwrite the module that it automatically mapped for you with the module that you want to execute from memory. Then, when you execute from that section of memory, it appears like you're executing from file-backed memory. So we have a couple of ways to do this. You can either pass in a byte array, or you can pass in a file on disk. It'll do that overloading for you. Go ahead. So to walk through this in more detail, first of all, we choose a random, legitimately signed module in System32 or sysfile64. We call ntcreate section, pass in the file handle with a sec image. Then we take the payload, which is a byte array or whatever PE that you want to use for memory. We write P to the base address of the view of that section, and then do all the normal virtualization and module mapping. The end result looks something like this, where you have in red the module that we mapped, and in blue the original version of user32.dll. So this is Mimikatz running from what appears to be memory backed by user32.dll on disk. As you can see from the addresses, the entry point of Mimikatz is in the one that we manually mapped. Now, this is actually a good screenshot because it shows some of the anomalies that can be a result of module overloading, which is specifically that in this case we have 2 copies of user32.dll in the process. That's not normal. You have the one that is normally mapped in the process when the process is created. You shouldn't have a second one, especially with that second one not being referenced in the loaded module list in the process. So the mere fact that you have 2 copies of this DLL loaded into memory is a pretty good indicator.
Yeah, okay. So the Wover kind of talked about a process injection technique, kind of. You may get back something like this. Some of them are holistic techniques like reflective loading and doppelganging. Others are execution methods like set Windows hookx, set thread context, ntcreate threadx, etc. Some of them are ways to pass data between processes, like, for example, with WNF states, like you can push data to a state and then read it in another process, or atom bombing, where you create a global atom and read it in another process, right? None of those things are actually process injection. The reality is that you have allocation and execution primitives, and that's like a many-to-many relationship, right? Also not totally accurate because you have primitives that allocate, that write and execute, but we're simplifying here. You can see some examples at the top there, and they're not totally important, but what I want to say is that on each side, they can kind of extend and be more complex than they're shown here. So as an example, you could use ntallocate virtual memory to allocate some memory. You write your payload in there, and then you want to use an APC to execute it. but the problem is with reliability. Are you going to have to wait for that APC to fire? So you do something more complicated. For example, you call nt-create threadx, and you create a thread at RTL exit user thread. So when that thread runs, it'll just exit, but the thread is currently suspended, right? And then you queue your APC on top of it with nt queue APC thread, and then when you resume the thread, it executes the payload and then exits gracefully, right? So things can be more complex than they appear here, okay? So the reality is that process injection is just a set of it's an assembly line of components that you can kind of put together in whatever way you prefer. And any components that we put into Sharpsploit give users flexibility on how they want to do things. Now, currently, those building blocks are limited, but we'll put some more in there over time, right? And then you have a pick your own adventure or poison type storyline, okay? This approach is similar to Pinjectra, if anybody watched that presentation from BlueHat last year.
So we had a few design goals for building a process injection API. Primarily, we wanted it to be modular, extensible, and simple to use. Like we don't have it separated into allocation, write, and execution. We just have allocation and execution. Partly because it doesn't always matter what write primitive you use for each allocation primitive. So we built an API that allows you to just combine these different components and build your own injector on the fly. So specifically, we have a payload type, we have an execution technique, and we have an allocation technique. And these can be implemented in different subclasses. So by default, we have a PIC payload, a position-independent code, which would be shellcode. We have, for execution, we have remote thread creation. And then for allocation, we have section mapping. The key is that the functionality for each of these is implemented in subclasses, and it's called dynamically via polymorphism. So to walk through the examples that we have so far, we have section mapping, which creates a new section that's not backed by anything on disk, maps a view of that section to the current process, writes the payload into the current view of that section, then maps a view of that section to a different process, and now the payload is available in the target process without ever actually writing to that target process. For execution, we have remote thread creation. So one thing that we wanted to make sure when we designed this API was that every technique that we implement here has as many options exposed to the user as possible. So ideally, even the operator can decide at runtime, as they're doing an operation, what techniques that they want to use in order to execute each post-exploitation payload. So for remote thread creation, we don't just have one technique or one API call, like create remote thread. We have create remote thread, RTL create user thread, nt create threadx, etc. So to build an injector, all you have to do is instantiate a class of the payload type that you want, instantiate a class of the allocation and the execution techniques that you want, pass in the options, and you call injector.inject, pass them in, and voila, it magically calls all of the functions defined in each of those classes and performs the injection in whatever process you specify. We're actually going to have this demo available when we release the blog posts, and we'll show using Covenant, which has Sharpsploit loaded, we'll show how you can have access to a target and be able to, in memory, on the fly, build an injector. So the key point there is, say you're a red teamer and you're doing an operation, and you're in an environment where they have some anti-malware or EDR that's catching the injection technique that's built in by default to your tool. Well, if you have this sort of modular process injection API, you can literally on the fly, in less than 5 minutes, build a new injector by assembling these components, keep trying them out until one of them works.
Yeah, okay, so I'm a defender as well, okay, not just an attacker. So I want to talk about detection strategies. Now, unfortunately, maybe you can imagine, but it's not all like sunshine, lollipops, and rainbows, okay? But we can try to do some things to detect this type of tradecraft. So since we're talking about .NET specifically and our tooling is in .NET, one of the core things we should do is correlate module load events, okay? So If attackers are injecting .NET assemblies into processes, like with execute assembly in Cobalt Strike, and those processes don't usually have the CLR loaded, that's going to create a lot of module load events, okay? So here we can see, or maybe you can't really see, but this is Notepad pre-injection, okay? And then in a next step, we inject some shellcode which loads a .NET assembly, and then our message box pops here, and we can see that a whole bunch of modules get loaded into Notepad, like MS Core lib, MS Core E, MS Core JIT, all of that stuff, right? So if you have the ability to correlate module load events within your detection stack, you should definitely do that, because if you can filter out those cases where such behavior occurs naturally, you'll definitely find like a good concentration of evil, okay? However, it does require silent testing and FP tuning, obviously, because you will find many cases where that stuff happens naturally, right? And if you have clients and you've ever written any detection rules, you know that no matter how good your rule is, you'll always find a client who's doing some crazy stuff that you never thought about, which triggers your rule, right? Yeah, this is my favorite, to be honest, right? Microsoft Windows.NET Runtime. So there is an ETW provider for .NET, which has a lot of visibility into the runtime, okay? Now, the issue is that this provider is not really exposed to end users. However, programmatically, you can subscribe to it, right? There is no problem. So last year, I wrote a tool, Silk ETW, and later Silk Service, which is a service version of Silk. And you can subscribe to a provider or a set of providers and just hoover up all of that data, okay? So you have a lot of options to filter based on event types, opcodes, all of that stuff. And I also added support for Yara. So you can have a whole bunch of collectors defined and a whole set of Yara rules, and every time an event comes in, you scan it, right? So what we can see here is that I'm manually mapping Mimikatz, and then I wrote some Yara rules, which are detecting this behavior very well, right? We can see there are some rules for loading modules from disk, other ones which are specific to manual mapping in Sharpsploit, even other ones which are detecting some native function calls, and some suspicious IL method signatures, okay? Now, when we put our slides on GitHub, I'll upload all of those Yara rules so you can have a look at them, but the process to write this is really easy and straightforward. So AMSI for .NET 4.8, we already talked about this. This is a great addition to the AMSI family. If it's enabled, support is backported to 4.0. Anything below 4 is still like without telemetry, but hopefully you can, through policy, make sure that your users or certain user groups don't have those versions of .NET installed, okay? Just a side note here that I think everybody kind of knows that, but AMSI's attack surface remains intact. So if AMSI is monitoring a space which has the ability to read and write memory, then that space has the ability to brick AMSI essentially. So the challenge becomes to detect those operations where users are trying to make AMSI inoperable. But that's not to say anything bad about AMSI, okay? It's a great addition. Then, yeah, okay, application introspection. I like to term it like this because we're really talking about hooking. But a lot of defenders, when I talk about that, they look at me as if I'm mentioning something evil or some kind of taboo, or we're not those kind of defenders, we're not hooking our users, or something like that. But the reality is that hooking remains a very powerful tool. to detect suspicious API calls or sequences of calls or some kind of aberrant parameter usage. So if you have a heuristic which is like these 7 API calls happen and these 4 API calls have these weird parameters, then you know like something evil happened there, okay? The other thing that people usually don't mention when they talk about hooking for defense is that hooking inherently brings blocking capabilities to the table. So you're in line in the process, right? Once that heuristic triggers, you can just drop the API call and execution doesn't continue at that point. Or since you're executing from inside the process, you can do some post-detection mitigation actions, right? You can kill the process or some other more complicated heuristic. Here we can see it's another tool I wrote, Fermion. It's an Electron front end for Frida with like an integrated Monaco editor, so you have linting and stuff like that. But what I'm doing here essentially is installing 2 hooks, one for NT-write virtual memory and one for NT-create threadx. So what I'm doing here is basically anytime NT-write virtual memory occurs, I try to inspect that buffer and see if it's a PE, right? I check like MZ and then I read ELFA new to find where the PE header is, and then I check some magic bytes there. And then if that all checks out, I know like a PE was written to memory, and I tell the user, okay, wait, something not good is going on here, right? And I print out the architecture of the binary. I'm not sure if you can really read that, and the entry point. Okay, and that entry point gets added to an array of entry points, and then later, anytime when NT-create threadx is called, I check the start address of that thread, and if it's part of that array, I know now that something bad definitely happened, right? First, P was allocated into memory, and then later a thread was created at the entry point of that P. Now, while this is like a simplistic heuristic that I wouldn't recommend anybody put into production, okay? But it didn't take a lot of time to develop that, and I'm sure that some more capable people in product can work on really good heuristics to detect some bad stuff, basically.
So how can you contribute? A lot of the APIs that we put into SharpSploit were specifically designed so that they can be built off of. And we encourage adding on new techniques. We will also provide a set of suggestions that we recommend, things that if we had the infinite amount of time in the world, we would develop and add into this giant library, but we don't. So we're going to have those if you want to contribute on the offensive side. But I also recommend that if you have detection strategies or techniques that you want to go, say, into our blog post when we announce this stuff, or you want to share with us or share with other people, we would greatly recommend and appreciate you reaching out to us on Twitter or in any other mechanism. We would be glad to credit you in our blog posts or however you would prefer. So in conclusion, the release for all of this stuff will be coordinated approximately around when the video goes up, maybe a little bit after, and we'll also release blog posts along with more details covering the deinvoke API, the process injection API, module overloading separately. And in the meantime, all of the code that we have available right now is in a PR to the main GitHub repo, so it's being approved this week, hopefully. But either way, you can go look at the code right now if you want to.
Yeah, we dropped like 3,000 lines of code on the maintainer, so he needs some time to look at that. Yeah, I just want to say as well that when we put our slides on GitHub, and at that point I'll add those Yara rules and how you can set up SilkETW, and also add any JavaScript hooks for Frida that you can run and test out, you know, those kind of detections. Okay?
Other than that, I think that's all we've got.
That's all we've got.
Thank you very much for having us.
Thank you.